Hello everybody, welcome to the first STEM webinar for this fall semester. So today our speaker is Lukas Heinrich. Lukas is from Technical University of Munich. He's a particle physicist and also a professor of data science in physics. So he's been a member of the Atlas experiment at CERN for a long time. He has been focusing on searches of new physics beyond the standard model. In addition to physics, he is interested in computational, statistical, and machine learning methods research, especially with applications in physics. He's, for example, well known for his work on differentiable programming for Heinrich physics and machine learning for systematics in Heinrich physics, and many other topics at the intersection of kind of data science and Heinrich physics in particular. So today he will be giving us an overview of systematic uncertainties in particle physics. So you see here, the title of his talk is Systematics in Heinrich Physics, Event Selection, Limits, and Discovery. So Lukas, please go ahead.
Yeah, thanks a lot for this invitation. I'm very happy to meet again with you and talk a bit about Heinrich Physics. So I assume that's kind of not a Heinrich Physics audience, but more a statistics audience. So I'm hoping I'm making it accessible, but if there are any questions, please stop me and then just let me know. And so I wanted to kind of start off with like an anniversary that we've seen this year, which is kind of interesting. This year we had the 10-year anniversary of the discovery of the Higgs boson. And so for physicists, this was, of course, like a huge breakthrough in the sense that it kind of completed, or we found like the missing particle of one of the major theories that explains nature. And so in that sense, from a physics point of view, it was a big day. But at the same time, I think it's also kind of from the statistics point of view, kind of like a culmination of a lot of methodological developments that happened within LHC statistics, within particle physics statistics over multiple decades. And I think the LHC experiments that discovered the Higgs boson were, kind of reached a new level of statistical sophistication in the sense of, how complex the models were that were required in order to kind of announce this discovery of the Higgs boson. And so on the right-hand side, you see our famous kind of 5 sigma discovery plot. So you can see this was, how we rejected our null hypothesis that the Higgs did not exist. And so that was, and so it's a simple plot, but there's a lot of things that kind of go on behind the scenes. And in this talk, I wanted to kind of give a bit of a feel how these types of results come about, how we do the modeling, and then maybe also, if we have time, kind of go into, how we can use machine learning in the future to, disrupt a bit kind of this standard methodology that we've developed over multiple decades. So the goal for this talk, I'll basically try to summarize how we build statistical models at the LHC, and especially how we incorporate Nugent's parameters. I'll describe kind of the current practice that we have for developing statistical tests, and discuss some of the kind of common assumptions that we have made during inference. And then I'll basically focus a bit on the frequentist point of view, because this is the dominant kind of statistical school within particle physics, and especially at the Large Hadron Collider. And so I'm assuming that people are more familiar with the statistical side of things, but less with Heinrich physics. And so I'll kind of start with introducing a bit. So of course, I'm sure many of you have heard about the Large Hadron Collider. It's a big particle accelerator at CERN, and it's 27 kilometers in circumference. And basically, it's a machine that accelerates protons, so hydrogen nuclei, to almost the speed of light. And so we have 2 beams. One is going clockwise, the other one is going counterclockwise. And then we use magnets to basically accelerate and bend the beams into the circular shape. And so they will kind of race around this track. And then at these 4 points that you see, CMS, Atlas, and LHCb, they're basically colliding head on. And so here you see the tunnel. So this is 100 meters underground. And so the blue thing is kind of like a very strong magnet that is able to bend the particle beam, even though it's going at a very, very high speed. And as we're going through, at certain points, the beams collide head on, and this is what it looks like. And so here is kind of like a particle collision, and around this particle collision point where the beams collide and produce like a spray of new particles, we've basically constructed essentially something like a giant three-dimensional camera that is capturing from every which angle, what is happening during these collisions. And so this is essentially the raw data that we are reading out and that we're aiming to analyze in order to find something out about kind of the core nature, about the building blocks of nature, and what the elementary forces are that govern our physical laws. And so this is basically our data generating mechanism. And as physicists, what we would like to do is basically we want to use the data to learn something about physical theory. And so if you would take like a Bayesian point of view, you can just write down Bayesian's Bayes theorem, and we have our data generating mechanism. So we have the data given theory, our theorist friends. So we are experimentalists, but we have of course many collaborators that think about which theories make sense and which theories make not sense. And so that kind of might be reflected into like a vague prior what theories are viable. And out of these two things, so the theoretical side of things and the experimental side of things, we basically want to synthesize knowledge on how we can what the data tells us about which theories remain viable and which theories are basically excluded. Okay, so that's kind of what we would like to do. And the first thing that you need to do is basically figure out, okay, how do you describe the data generating mechanism? What is the forward model of the data? And so we want to somehow connect the theory part with the data. And the problem here is that the forward model is pretty complicated. So there's the theory is described at very, very high energies. And then the information is spread across hundreds of millions of different readout channels. So we need to think about how to describe this forward process and how to model this. And one of the nice things about fundamental physics is that we have extremely strong foundational knowledge on what the forward modeling process looks like. So we know through decades of discovery and so on exactly what is happening as we kind of translate from this formula to the 100 million channels that we have in the detector. And so basically what we can do is we can describe it as a very deep Markov model that is like a generative process. So we can describe what really happens at the point of collision. And so then kind of like an initial set of particle gets created. And so we can calculate using quantum field theory the probabilities of these different combinations or configurations of particles. As the particles are basically moving outwards through the detector, we can describe a lot of different processes where there are decays of particles and particles radiate other particles and so on. They move within like strong force fields. And so this is what's shown kind of in the middle of the picture. And depending on that type of evolution, some particles survive all of these processes and hit the detector or start interacting with this camera material. And so this is what you can see kind of on the left-hand side of the screen. So you see like a particle shooting into a detector, interacting vigorously with the material. And at the end of this interaction, you actually see the observed voltages. So this is the data that we're actually reading out from the readout electronics. And so that's really nice. So we know what the forward model looks like. It's very powerful. But there's a caveat, because unfortunately, all of this evolution that we kind of know about theoretically is latent. So this is not something that we observe. And all we get kind of as experimentalists is, we see the voltages that happen, at the very end. So this is the stuff that we read out. But all these intermediate steps that are part of this Markov, graph are things that we're not observing. And so this is stuff that we need to integrate over. And so if you wanted to write down kind of what the likelihood is of like any particular event as we're observing it in the detector, it's going to be very difficult, because this is an integral that is at least hundreds of millions of dimension, and it's completely intractable to solve it. And so particle physics is in that sense a completely likelihood free problem. There's no way to even have like an approximate version on what this high dimensional likelihood looks like. So just as a reminder, X here is basically, we have 100 million different sensors in this camera. And so we would need to describe 100 million dimensional likelihood data space with this likelihood. And so this is completely intractable. And this really kind of is the core of the problems that we have in particle physics. Then there's one more issue. So the data side, so if you look at the likelihood, so you have px of given theta. So the data side is already pretty complicated, but the parameter side is also pretty complicated. So this is already a pretty rosy picture. Actually, what is happening is that the theory space is not only kind of the space of core theoretical parameters, like does the Higgs boson exist? How does it interact with electrons and so on? So these are really kind of core physics parameters. But actually, in this latent, Markov process, every type of transition probability comes with its own set of parameters, and so these, of course, affect the data. But there are parameters of low energy physics that don't really have anything to do with the stuff that we are interested about in doing inference on. And so these parameters are, in that sense, Nugent's parameters. They're really necessary in order to model the data, but they're not parameters that we're really kind of interested in, producing, for example, confidence intervals and so on. And so this is, necessary, but it complexifies the model quite a bit. And so if you would look here, basically, at the relation in the kind of parameter vector, you can see, so we have, maybe like a implicit likelihood that is defined through this forward model. And so that has some parameters, but the core physics parameters, there may be kind of order 1 to 10, or maybe up to 100. And then Nugent's parameters, we have hundreds and hundreds of thousands of Nugent's parameters that really kind of affect what the data looks like, but are really just knobs that we need to describe the data, not kind of our inference target. And so this type of imbalance is challenging, and so we need to somehow find ways to constrain all of these Nugent's parameters and deal with them. And then we also need to kind of adjust our inference methods in a way that we can produce results that excise these Nugent's parameters from the way that we present the results, because this is usually not something that people are interested in kind of reading about. And so in a Bayesian point of view, for example, you would marginalize out those parameters, and I'll talk about basically what we do in a frequentist sense. And okay, so that sounds pretty bleak. We have complicated data, we have complicated parameters, we have a completely intractable likelihood. And so, but of course, we're still doing science, and the question is, okay, how is that happening? If we don't have a likelihood, we can't just stick it into the Bayes theorem and run, for example, MCMC. And so really the saving grace of all of this is basically simulators. Simulators are basically computer programs that are where we encode all of our domain knowledge of this forward modeling and into computer code. And then with these simulators, we can generate synthetic data that looks very much like the data that we're actually taking, like on the detector side of things. And so what does this look like? We can basically, start our simulators with a certain set of parameters. And because we know the microscopic transition probabilities very well, we know what the modeling looks like. We can basically sample from this Markov process very easily. So starting from the core physics parameters, we can sample kind of the initial configuration of the particles in the collision. Once we have those initial particles, we can stochastically forward model them as they're decaying, and maybe they're scattering off some atomic nucleus and so on. And that produces this parton shower. And then we have a very detailed digital version of our detector that is standing 100 meters underground. And we know exactly what the composition is in terms of materials, what the geometry of the volumes is. And so we can really track individual particles in the kind of time step type of way as they stochastically interact with this detector material. And so this, in those simulators, we have all the low energy physics encoded, and it's all kind of like a stochastic forward process. At the end, we even simulate all the detector readouts and readout electronics, and then which is also a stochastic process, whether or not the module lights up, yes or no. And then in the end, we get like 100 million numbers back, what the state of the detector would be after this simulated event has passed through the detector. And so while we cannot evaluate the likelihood, because the integral is intractable, because we know the integrand very well, we can very easily sample from the likelihood. And so that is really kind of the core setup of likelihood-free inference. And so I'll talk a bit about what we do in the next couple of slides. Okay, so here's just a slide on kind of how good these simulators are. So there's decades of experience that is has gone into coding up these simulators, and these simulators are really where all of our domain knowledge sits. And so you can see here kind of the data as we're taking it at the LHC. So these are the black dots, and then you can see kind of like a density estimate on how these black dots are, how these events are distributed. And so you can see that on the left-hand side, this is a log scale. You can see this is distributed over 7 orders of magnitude. And we have an extremely precise modeling of these types of events thanks to our simulator. So all these colored densities, so basically this is a mixture model, which I'll discuss kind of later in more detail. But so this is it's a mixture model. You have these different components. They're all different ways to simulate events. And then they describe the data very, very well. And so these colors are basically all different theoretical settings. And so these simulators are really, really high quality, and they allow us to do a pretty precise likelihood-free inference, even though we have like an intractable likelihood. Okay, one interesting coincidence, or maybe not so coincidence, is that also high-energy physics is one of the major domains kind of in fundamental science, where the main statistical school of thought is frequentist statistics. So most of the results are kind of presented in the frequentist way, even though people appreciate the Bayesian point of view, of course, and but there are different kind of cultural reasons, maybe why frequentist statistics has kind of still its foothold. One possible reason that is kind of interesting in this story is that frequentist statistics, if you think about it, is really fundamentally more amenable to likelihood-free inference. And so if you think about hypothesis testing, you really don't need to evaluate the likelihood. So hypothesis testing and the frequentist setup, is all about knowing this or modeling the sampling distributions under a test statistic. And so you need to be able to sample from the forward model. So we established that we can do this. And then you need to be able to evaluate the test statistic. And so, depending on how complicated you want to make your test statistic, that might or might not require knowing the likelihood. But fundamentally, there's nothing that kind of forces you to know the likelihood per se. And so that is really interesting, and it's something that I'll get back to later on. So on the right-hand side, you get like a bit of a cartoon on frequentist statistics. So you have a high-dimensional data space that gets projected down into a summary statistic where you have then density estimates of the summary statistics under the different hypotheses. And then depending on where you do your threshold, you can have hypothesis tests of different size, and there's a trade-off between size and power. And then you can cast this into a p-value, and then you have your test result, and so on. And so this does really require evaluating the likelihood per se. And so given that we have this freedom of kind of choosing our test statistic freely, we use this in particle physics to basically think about how we can compress the data. And so we have the data generating process generates like 100 million dimensional vector of floats, for example, different voltages and so on. And this is, of course, not really interpretable to a physicist. And so a lot of what we do in particle physics, is trying to cast these individual voltages into a language that a physicist can understand during the analysis. So we want to reconstruct individual particles. We want to describe the event as in a form where we can say, okay, there's a particle moving this way, there's a particle moving that way, and so on. And so we generate lower dimensional representations of the data that are more interpretable. And then this is roughly, tries to do like a step-by-step inversion of the forward modeling process. So the forward modeling process is diluting the data by branching more and more. And by kind of iterative clustering, we're trying to find like a good compression of the data, which then leads us ultimately to a good test statistic that we can then do our frequentist tests on. And so on the right-hand side, you see like a successful example of that. So this is exactly the Higgs discovery. And so this is basically converting 100 million numbers into a single observable, where you can really see in the red the peak of the Higgs. And so this is where you can see that the Higgs exists even without doing any sophisticated statistical tests. Okay, so but then of course likelihoods are still useful. Even if you do frequentist analysis, you do use the likelihood quite a bit. And so why is that? Because of course we don't want to use any test statistic, we want to use good test statistics. And so the classic Nyman-Pearson lemma then tells us that for an optimal binary test, we at least need to be able to evaluate the likelihood ratio, for example, for two hypotheses. And so in order, like the easiest way to evaluate the likelihood ratio is to be able to evaluate the likelihood. And so if you can, somehow formulate your problem in a way where you have like a, evaluatable likelihood, that is useful, because then you can construct this optimal test statistic, and then you know that you're roughly making the most use of the data that you can. And so, completely giving up on likelihoods is, for a long time, like didn't look like something that we should be doing. And so a lot of the particle physics inference pipeline is basically about finding kind of like a proxy likelihood or an approximate version of the likelihood that we can then stick into the standard statistical inference pipeline as you would have it from a textbook example. Okay, so this is then the usual workflow. So basically what we try to do is, so instead of modeling the full likelihood, which is, like 100 million dimensional data vector, we try to at least model the likelihood or the density of a low dimensional representation of the data. So we try to do a lot of work to not lose a lot of statistical power by doing this compression. But of course, the data processing inequality tells us that we will, undoubtedly lose information. But we try our best to not do that. And then we have a low dimensional representation of the data. Density estimation in low dimension, at least, is something that you can do in a likelihood free way using, for example, just samples from a simulator. So you can do something, for example, like a histogram. If you have a one-dimensional test statistic, a histogram is essentially the way that you could, for example, approximate the likelihood in this lower dimensional space. And so the standard setup is, okay, we have our raw data and simulated samples on the right-hand side, and then we stick it through kind of to be optimized summary statistic that gives us a low dimensional representation of the data and the simulated samples. From this, we do a density estimation based on these summary statistics. And then once we have a density, we can use all the standard tooling for statistics and do test statistics based on these density estimates, like likelihood ratios, and then we can generate p-values. And this is exactly kind of the workflow that generates, for example, the p-value of the Higgs discovery that you see on the left-hand side. And so really most of the work goes into carefully building this approximate likelihood based on samples and this stuff that we get out of the simulator. And so there's been lots of interest in the kind of more likelihood-free methods. And so I hope I get to this point at the end of the talk. There's not only disadvantages with this workflow. So one of the disadvantages, of course, is that by compressing the data into like a low dimensional representation, you lose sensitivity. You're not making full use of the data. There might be correlations in the high dimensional space that you lose by doing the compression. But actually it could also be a blessing. And so this is something that we use a lot. So there's, of course, because you have simulators, they might not be perfect. And by the same token, where you lose sensitivity or lose correlations, you might also lose on purpose correlations that you're not interested in. And so there are certain things where we want our results to look in a different, like in a certain way, where, for example, we want to have robustness of our results against Nugent's parameters. We want to maybe shape the likelihood, in a certain way where, maybe we don't have a strong correlation on what the confidence sets look like in the parameter of interest and the Nugent's parameter dimensions. And by picking our data compression algorithm in a certain way, we can essentially mold the likelihood in a way that will always be bigger than the full use of the data, but maybe it might be shaped in a nicer way where some of the things that you might not be able to model correctly with the simulator are you're not even attempting to model that. And so you can it's a kind of a question of designing the compression algorithm in a way to match these desiderata that you might have kind of from a priori physics perspective. Okay, so here's an example of what this looked like. And so it's also one way where machine learning really plays a big role. So this compression algorithm is something that we can kind of choose freely. And so we can use machine learning to do this compression. And so it's we can use machine to do this like planned degradation of this broadening of the confidence sets. And so here's an example where you can basically find representations of the data where if you run the simulator at certain parameter points and you plot the sampling distributions of like a specific low dimensional representation of the data, typically if the simulator was run with different parameters, that sampling distribution might look different. But if you you can train machine learning algorithms, for example, to explicitly hide these differences in sampling distributions and basically get sampling distributions that are invariant with respect to certain parameter dimensions of the simulator. And so this is something that we sometimes call like controlling background distributions. And so on the right hand side, so this is you can see this was used in the search for new particles that are expected from supersymmetry. And so here we want to really control what the sampling distributions look like, and we want to not be sensitive to certain changes in the theory. And so here we basically use, for example, machine learning to find pivotal quantities that are on purpose, maybe trading off ultimate sensitivity to kind of the parameters of interest. But what you gain is some robustness of the result. And so that's a pretty active area of research. Okay, so then I wanted to talk a bit about how we build this approximate likelihood model. So as I said, even though frequentist statistics doesn't require it, we can roughly try to get like an approximate likelihood in order to be able to use all the standard tooling that we have from statistics. And so really this is where most of the work is done in particle physics. And so the first decision that you need to make is kind of what type of style of likelihood you want. And so kind of at the core, the data set that we get is basically an IID data set. So we have collisions every 40 million times per second. We have a collision, and we assume that the outcome of that collision is an IID sample of the overall state of nature, which is kind of implemented as a generative model. And so we have like a set of events, and so that is like a like an IID sample of individual events, and each of those samples kind of comes with its own with the same likelihood. And so the kind of most kind of extraction of information happens if you just model it exactly in that way. And so this is what we call like an unbinned model. But then because we have many events, and so because we have these 40 million events per second, we can also kind of combine these events into something like a histogram and bin and collect very similar events kind of and just do like a counting experiment. And this is then what we call like a bin model. And so this is more or less equivalent to an unbinned analysis where the particle in the density in this low dimensional space is stepwise. And if we have lots, so typically when we have limited statistics, so we're trying to discover like a rare process, this happens with an unbinned model. Once you accumulate enough statistics and the binning doesn't have a big effect, then we usually go for this binned approach, because that is computationally much easier to handle. And then once you start building the model, one thing to keep in mind is that at the very core, particle physics will be a mixture model, because quantum mechanics doesn't allow us to really predict exactly what is going to happen for every single collision, but there's usually like a finite set of choices on how these collisions can happen. And so, for example, on the left-hand side, you see like an event where you have 4 particles shooting out. And so you can kind of enumerate how many ways could there be to have a collision where you have these 4 kind of high energetic particles shooting out. And on the right-hand side, you see 4 possible solutions. So you have 3 solutions that don't have a Higgs boson anywhere. And then on the lower left-hand side, you see a version that has a Higgs in the middle. So this H is a Higgs. And so you can basically describe all of particle physics as a type of mixture model where the strengths of the individual components of the mixture are then also modulated by the parameters of the theory. So, different masses of the Higgs boson would, imply different strength of that particular component in this mixture model. Okay, so then once you have this mixture model, one useful categorization is that you have like signal and background components. So this is, you have here in this plot, for example, 5 different mixture components, but then most of them are, background. So these are things that you're maybe not really looking for, but you need these components in order to describe the data. And then on the right-hand side, you see like 3 versions of the final component, which is the signal in these outline histograms. And so what is the difference between background models, background components and signal components? So the background components are really only affected by the nuisance parameters, while the signal component is affected by the nuisance parameters and the parameters of interest. So the signal is generated by the things that we're really interested in, kind of in the parameter vector, like the mass of the Higgs or the mass of this particular event. You can see, depending on what the mass of this hypothetical particle is, it will modulate the position of this peak in the distribution. But the background really is only affected by the nuisance parameter. So this is like a categorization that makes a lot of sense for us as physicists. And then, one of the problems in the simulation-based inference is that, so we can do have very good simulators, but getting, for example, the density out of the simulator requires, running many samples in order to populate the histogram. And so if you want to do something like a maximum likelihood estimate, so for like a single point in parameter space, you need to run 10,000 CPU hours in order to populate the histogram. And so just evaluating, or getting what the shape of the histogram is for a specific parameter is incredibly expensive. And so doing like something continuous, like a gradient descent or maximum likelihood search and so on, it's not really possible, because then you take a step in the parameter space, and then you need to recompute 10,000 CPU hours in order to see what the histogram looks like and what the likelihood at that point looks like. So this is not really an option. So you need to have some way to do a much faster job in order, instead of like for every particular parameter point, evaluating the simulator. And so the key here is then basically interpolation. And so this is then what we do. So if you kind of focus in on like one particular bin of this density, that's estimated through a histogram, you can see, so the different theories. So we have this W prime. So this is for different parameter points. So so the tera electron volt, this is like a mass value. So how heavy this particle is. So you have 3, 4, and 5. And then you can see, depending on what the parameter value is, the height of this bin, so the density at that point changes. And so we can maybe afford to run the simulator 3 times. But then if we want to, of course, we might be interested in, okay, what's the maximum likelihood estimate of this mass? And then that requires doing gradient descent. And so here, what we try to do, we try to build like an interpolation mechanism that allows us to smoothly interpolate between these individual histograms or density estimates as we're walking through the parameter space. And so one of the big issues that we have is deciding on how do we populate initially the parameter space in order to get like a good interpolation. So this is a problem that is relatively unsolved for us. Okay, then the next step is, so you kind of know how you're describing your key measurement, and what the next step is then incorporating prior information. So as I said, the high geophysics analysis is really dominated by Nugent's parameters, and so we need to incorporate prior information. But we want to do it in a way that allows both frequentist and Bayesian treatment. And so, of course, even though we're doing a frequentist analysis, we need to incorporate all of this prior information. And so you can kind of develop this quite easily if you had like as a Bayesian like some kind of prior, and then you can ask yourself, okay, where does this prior come from? And most of the time, your prior belief might come from like a prior measurement. And so actually, that prior is connected to some data. And once you resolve this through Bayes' theorem, you of course have like a likelihood that is associated to this data, and there might be so that this prior is actually the posterior of other measurement, and so this is what we call a subsidiary measurement, and the prior then is a result of that measurement with the prior that was used at that iteration of the experiment, and so that is something we call the Ur prior, and so it's like 2 generations before your current measurement. And so if you do a frequentist analysis, you're just collecting basically the subsidiary measurement as an additional term in the likelihood, and then you just model the full, both your current measurement and the other measurement that provides some information about the Nugent's parameters into like a full joint statistical analysis. And so basically a lot of the tooling that we have in particle physics is about sharing different fragments of a likelihood in a kind of specific serialized form so that we can email it around and people can send these fragments, and other people can use that in order to incorporate that as additional information into their statistical analysis. So then the question is, okay, how do you get these subsidiary likelihoods? And there are kind of 2 degrees of sophistication here. So you can either have the gold standard, so actually kind of add into your likelihood like a full measurement, like a full-blown measurement that somebody else has done. Maybe they themselves have like a big likelihood with hundreds of Nugent's parameters and so on, and but they measured like a different part of the data space, and but that part of the data space might be informative about like a specific Nugent's parameters that you have to add to your model. And so by asking that person to provide you with their likelihood, you can just add it into your analysis. And so this is sometimes in high geophysics called like a control region. So it's, you have in this box, for example, all of the data. The main measurement that you're doing might be like this green area, but then in this green area, there might be some Nugent, the data distributions in that area might be affected by some Nugent's parameters. And by measuring like a different corner of the data space, you might be able to construct a likelihood that is able to constrain like specific parts of the model quite powerfully, maybe because they have higher statistics. And then you can provide this combined likelihood. And so on the left-hand side here, you can see that you have that you're a signal region where you have the signal component, and in red you have like a specific background component, and that is affected by some Nugent's parameter, like what is exactly the shape of that background component, for example. And by going into a corner of the data space where there's lots of these events for that specific component, you can really collect a lot of statistics and constraining power in order to model this specific component. And by just doing a joint measurement, this is then how you control the Nugent's parameters. And so that's ideally what you would want to do, but this really requires to get like the full likelihood, that is like an entirely separate analysis, and very often that is not possible. And so we sometimes also do kind of like a shortcut where we have these kind of simplified subsidiary terms, where if there's no full likelihood available for this additional measurement, we try to approximate it by basically assuming asymptotics and estimating the effect to the likelihood as a type of constraint term, where we model it basically as a likelihood in the estimator space that is a result of the data, and having that as a kind of Gaussian likelihood, for example, as a constraint term. And so instead of having like a full likelihood term, we just add like a Gaussian constraint term, but it acts kind of as in the same way as the full likelihood would act under the assumption that the asymptotics would hold. Okay, so then we basically have all the different pieces. So we have a way to kind of model our data. We do density estimation. We know how to evaluate the data at a point where we maybe didn't run the simulator. We can know, how the different Nugent's parameters affect the distribution by interpolation. And we know how to add like all the different kind of prior information that we have about the Nugent's parameters from other measurements into the likelihood as well. And so in the end, if you put everything together, this is then kind of what it looks like. So this is like a shape of the likelihood that is surprisingly versatile in high energy physics, where you basically have like a series of Poisson measurements which originate from like this histogram-based modeling of this binned likelihood. And then you have additionally these constraint terms where you have all of these subsidiary measurements that constrain specific Nugent's parameters. And then if you look more closely into what an expected number of events is for like a specific point in this one-dimensional distribution, you get this mixture of different components and then these interpolation factors. And what's kind of interesting that you can roughly estimate that a very large fraction of kind of scientific results at the Large Hadron Collider use exactly this simple shape of the likelihood. And the reason why that works is that because most of the physics really happens kind of in the projection space or in the projection step of finding these summary statistics, and then the ultimate statistical model that you build out of these summary statistics is usually just a series of Poisson terms, and then whatever you use for subsidiary measurements, which might be, for example, these Gaussian terms or also Poisson terms. And so there's common tooling available, and so this is something that I, for example, work on, and people basically can use all of these different building blocks in order to build up the likelihood that they have. And so this is what underlies, for example, the Higgs discovery as well. Okay, so then we have a model, and now we want to do statistical inference. And so we can kind of see how this works. And so I'll be quick here. So basically what we have in particle physics is that we have nested models. So as a reminder, we're not really interested in doing inference on the Nugent's parameters. And so the way that we split up our parameter space into hypothesis spaces, so what is the null hypothesis, what collection of parameters is our alternative hypothesis. So we basically have composite hypotheses and specifically nested ones, where the null hypothesis is a subset of the parameters that are possible for like the full parameter space, and these null hypotheses are indexed only by the parameters of interest. And so if we have like the space of parameter of interest and Nugent's parameters, we have like a slice for like a specific set of parameter of interest that we specify as the null hypothesis, and this is how we want to do inference. And then after kind of multiple decades of iteration, high energy physics really landed on the kind of classic likelihood ratio test, which is also has optimality properties, as was shown by Wald, in the 40s. And so in our lingo, so we call this the profile likelihood ratio. And basically the idea is that you just for every hypothesis set, you kind of pick the best in class, so the maximum likelihood for that specific subset of parameters. And so for the alternative, you can just do like a global optimization, whereas for the null hypothesis, you need to stay within the slice, but you can optimize the Nugent's parameters. And once you have these kind of proxy parameter points for each of these hypotheses, that we take the likelihood ratio and then this is our test statistic, and that test statistic only depends on the parameters of interest, which is nice because it's exactly the way that we want to do our inference, just as a function of the parameters of interest and not as a function of the Nugent's parameters. And then we just proceed with the standard kind of statistics where we try to develop estimates of the sampling distributions of the test statistic. And so while we could do this in the sampling-based way, where we just accumulate samples of the test statistics and do density estimation, in practice we rely very heavily on the asymptotic theory on kind of what the test statistic distribution looks like. It turns out that particle physics then, once you did all this compression and approximation of the likelihood, very often kind of stays within the assumptions of the asymptotic theory, and then we use kind of Wilks theorem and Wald's asymptotic theory in order to do our inference, and then you can estimate what the sampling distribution is for these test statistics. Very often they will be kind of chi-square. There's one kind of slight modification to this, where in particle physics very often our theories, our null hypothesis, for example, lies at the boundary of the parameter space, because if you have the strength of the component of new physics is 0, that is basically the same as having no new physics, and so this is our null hypothesis. And so then you need to adjust a bit kind of what exactly these sampling distributions are, but you can do it in closed form. And so this is very often kind of what we use in particle physics. And then in interval, if we want to do, for example, interval construction, I would say Heinrich physics is actually fairly principled. I had an interesting discussion with Mika about Nyman constructions and so on. And so Heinrich physics doesn't budge here, and we actually do like a strict Nyman construction in order to do our frequentist intervals. And so here we do one little shortcut where we assume that because we use, for example, asymptotic theory, we assume that the sampling distributions of the test statistic only depend on the parameter of interest, so that we don't need to do the Nyman construction in the full parameter space, but we can only do it, or we can get away with just doing it in the parameter of interest space without having any loss of coverage. And this works if you're really kind of in a space where all of the assumptions of asymptotics hold. And it's something that is rarely checked, but you really gain a lot computationally, because as we said in the beginning, there are many, many fewer parameters with interest in Nugent's parameters. So if you can get away with doing the Nyman construction, I mean, doing a Nyman construction at 1,000 dimension is completely hopeless, and but doing it in 1 dimension is very, very possible. Okay, so then that's kind of interval construction. So this really kind of is like a short overview over like the methodology that we had at the LHC, and this really kind of drove us over the last couple of decades of development and really supported, for example, the Higgs discovery. And so thousands of results were kind of generated using this methodology. And so you can kind of think about, okay, after developing all of this, are we done? And so we just kind of turn the crank. We find different ways to compress the data, but like the core methodology is fixed. And but in some sense, yes, but there's a way where you can kind of go beyond that type of methodology using machine learning. So I'll only talk about this very briefly just to give a taste, and I'm happy to discuss later on. And so we can really go
Lucas,
back.
just a quick note that you have about, let's say, 8 or 9 minutes left.
Yeah, that's fine. And so you can kind of go back to the basics and say, okay, in frequentist analysis, we really don't need the likelihood. We kind of chose to model a likelihood in order to kind of turn like a likelihood-free inference problem into like a likelihood full problem, which is in some ways easier to reason about, but you really don't need it kind of fundamentally. So we have like all these different steps. We have the data, we're compressing the data, we model like a low dimensional density using density estimation. We then have likelihood ratios, we do profiling, we get our confidence intervals and so on. And so all these intermediate steps are actually optional kind of from a frequentist point of view. And so recently there was a lot of development in exploring machine learning driven more direct likelihood free inference, where not insisting on having this very interpretable chain of intermediate steps, but you try to model more end-to-end in a kind of machine learning way. And so you can kind of think about like what the connection is between machine learning and frequentist inference. And it's really quite straightforward, where like a key statistics concept is likelihood ratio. And so why is it important? Because among all the functions that you could think of, that are candidate test statistics, the likelihood ratio is an optimal test statistic, according to the Neyman-Pearson lemma. And so it's kind of like an optimality property in the space of functions. And then machine learning, you can also so what is machine learning? In one sentence, is really good at searching through a function space for specific functions that are optimal in one sense or another. And so then you can kind of combine these things. Well, if the likelihood ratio is optimal, like in like a specific sense, it stands to reason that you can find it through optimization, right? And so how do you optimize in like a space of function? Then you would use machine learning. And so this is a really kind of close connection between doing machine learning and frequentist statistics or searching for test statistics. And this is something that has gained quite a bit of interest recently in particle physics, and is starting to shift this statistical methodology that seemed pretty frozen in a couple of years ago. And so this is then what is sometimes called the likelihood ratio trick. And so this is just an example of finding basically the Neyman-Pearson lemma through machine learning. And so this is here like, and okay, let me see if this should be animating. Yeah, so here basically what you can show is that, I mean, it's a well-known result that has been kind of around for a very long time, but you can show that training a neural network for classification, and if you plot the decision boundary, basically the decision boundary will be the likelihood ratio, right? And so by just doing or formulating the search for a good test statistic as a variational inference or variational search in the space of functions, you can find a likelihood ratio without formulating the individual like numerator or denominator. And once you do this, you can really start replacing a lot of the intermediate steps that you have in your statistics pipeline with like a pretty big block of machine learning. And so we had like this initial pipeline of data compression, approximate likelihood. And once you have this approximate likelihood, which had like all these interpolation and mixture model and all of these different things, you can replace that with basically something that directly spits out, given the data or like a specific event, that will spit out exactly the likelihood ratio. And then the only thing that is left to do is that you maybe do profiling, because you want to get the profile likelihood ratio in order to generate then the final inference results that are maybe the confidence limits or maximum likelihood estimates and so on. And what's important here or interesting to hear is that basically this removes this need for a data compression. And so we can recover some of the information that we have lost due to the data processing inequality, and really model much more high dimensional data that maybe we couldn't do with this density estimate approach, because it's very difficult to do like a histogram based density estimate in very high dimensions. And so this is kind of like a fairly new workflow or a new take on how to do frequentist inference in particle physics. And so this is like a new generation of tooling that is appearing in particle physics that tries to help users to train these likelihood ratio networks and skip the part of density estimation, goes directly to the ratio. And so there are different topics in also like differentiable programming and differentiable simulators that kind of help with this entire program of training these or finding these good test statistics in a machine learning driven way. And then so the last couple of slides is basically you can then once you start with replacing parts of the statistics workflow with blocks of machine learning, you can kind of think about, okay, how far can you push this, and how many steps of the classic statistics workflow can we replace with machine learning? And so in this model where we replace the likelihood or density modeling aspect directly with like a likelihood-free estimation of the likelihood ratio, then the only thing that kind of is the remnant of the classic statistics pipeline is the profiling step, and where you optimizing the likelihood ratio with with respect to specific parameters, and then you can ask yourself, okay, can you replace this as well? And basically the question is, okay, why do we use the profile likelihood ratio? It's exactly the same story. We use the profile likelihood ratio because it's optimal in a certain sense. And so if you are able to formulate this optimality property in a way that is amenable to machine learning, then you should also expect that you are able to find the profile likelihood ratio and not only the likelihood ratio just through variational optimization of a very highly parameterized family of functions, which might be, for example, neural networks. And so then basically what we would have is like a neural network that directly outputs this profile likelihood ratio. And so I'll just flash the slide. I'll not go into this. And the answer is yes, you can do this. And so you can actually find like a situation that if the profile likelihood ratio is optimal, then you can actually find it through optimization. And here's an example where you can show that by just using samples and like a machine learning training, you can find or plot the profile likelihood ratio without doing density estimation, without doing conditional optimization of the numerator or the denominator and so on, but it just basically works. And so this is fairly new. So we had a paper kind of recently, and so I'm happy to chat more. And this is something that I'm also working then on with Anne, and so this is very much connected to the likelihood-free frequentist inference program that Anne is running. And so then you can kind of see something that is coming within view or within reach, where you can really you start out with this classic pipeline of explicit modeling of approximate densities, and but by replacing step by step more and more steps of the statistical inference pipeline with machine learning, you can generate very robust frequentist results kind of in an end-to-end way using machine learning and using the samples differently than using them for like density estimation, but you use the samples in order to train the neural network that then will output directly the test statistic that you're looking for. Okay, so this brings me to a summary. So I think LHC statistics in the classical sense is a poster child for frequentist analysis in a fairly complex setting. So we are likelihood free, and so we can only sample from a simulator. The simulator is pretty expensive, and the data is very high dimensional. The parameter space is very high dimensional. We still kind of do quite, I think, solid frequentist inference. There are many decades of development that kind of resulted in this well-oiled machine of how we produce this results. And so this is partly also because of the nice collaboration with statisticians like Michael. And so the classic approach, I think, it's not going to change, and we're fairly confident, comfortable with this. And one thing that is emerging and has I think capacity to change the picture a bit on how we do statistics maybe in the next decade is by using machine learning to really find new formulations of likelihood-free inference. And so that's something that I'm excited, and let's see how where this goes. Okay, thank you very much.